105A was first flown in October 1955 and has accumulated well over 100 flights. It is presently being used to evaluate systems operations, such as the emergency hydraulic powered by a ram air turbine, which furnish satisfactory control power at landing and at supersonic speeds with engine cut. It has also successfully completed a drop program conducted by Special Weapons Center personnel. Both bluff and turnaround shapes have been dropped at speeds ranging from Mach 0.9 to 1.3 and altitudes from 8,000 to 35,000 feet. The ejection mechanism is pneumatic with an initial force of 8,000 pounds. A Labs release was also accomplished at Mach 0.92 and 4 Gs. Results of the program prove that repeated, predictable, and accurate ejections can be made at supersonic speeds. The B airplane will be used to further extend the speed regime. Pitch-up has been investigated by both company and Air Force pilots, and apparently the low stabilator has eliminated the problem. The B airplane was forced to make a belly landing on its first flight, due primarily to a nose gear retraction speed far faster than any experienced during hundreds of ground retraction tests. This excessive speed made the up-lock system malfunction, and the nose gear could not be extended. By December 1st, however, many modifications resulting from the A program were incorporated, and a total of 22 flights were accomplished. Emphasis has been placed upon evaluation of flying characteristics, such as stability and control, thermodynamic measurements to finalize the variable air inlet scheduling, and a gradual extension of top speed. Ultimate objective, of course, is to demonstrate ability to perform the tactical mission for which the weapon system was designed. This mission profile permits delivery of a special store 900 nautical miles from base and return with adequate fuel reserve. Utilizing a 105 buddy tanker, operating from the same base, only one in-air refueling will extend this radius almost 50%. This buddy system is based upon a standard 450-gallon external tank modified to carry a drogue and necessary actuating gear along with 230 gallons of fuel. This is carried on the centerline pylon, and the standard Bombay ferry tank is also used. All fuel can be transferred except that necessary for tanker to return to base. Optimum hookup is expected to be at 300 knots indicated at 32,000 feet. This extension puts effective radius well over 1,300 nautical miles. In-air refueling, together with the dispersion possibilities offered by the Zell system, make possible some interesting options analyses. The fire control system for the 105 has been flying for about 1.5 years in a modified RF-84F. Bombing modes were essentially completed by December 1st, and a production unit will be installed in the second B, expected to fly in January. Further development of the system is expected to provide automatic Labs capability. Data reduction so far gives every indication of a successful and timely production installation. 50% of all drops made at Eglin were within 500 feet CEP, and 75% were within 700 feet. Capability is provided for both gunnery and rocketry, air-to-air and air-to-ground, plus dive, level, and labs bombing. The ASW-10 automatic flight control system has also been under development at GE since 1954. Basic requirements were revised 4 times by a Republic GE WADC design team, and the present system has now been approved for production installation. An F-84F was used for stringent component testing. Flight test in the 105 will start in the spring of 1957 when air data computer becomes available. Both the A and the B airplanes were flown by Air Force pilots at very early stages and throughout the flight test program. The number of flights per month and total Air Force flights indicate good progress. After Phase 2 tests on the A, Air Force pilots made 29 recommendations. 17 of these have already been incorporated in test airplanes, 7 will be in early production airplanes, and the remaining 5 are in areas where solution will be made prior to delivery to tactical units. In the clean configuration, the B takes off in less than 3,000 feet, and best performance climb speed is about 1.2. True top speed has been extended over Mach 2, and the variable air inlet pressure measurements now being obtained will permit optimum positioning of inlet plugs and bleed doors to attain best pressure recovery for fast acceleration and more speed. At the present, all indications point toward a successful program. The F-105B is a high-performance fighter-bomber capable of carrying special weapons internally to facilitate delivery at maximum speeds. At maximum gross weight in the clean configuration, takeoff run is about 3,000 feet. From brake release to 40,000 takes 2 minutes, 42 seconds. Pratt & Whitney J75 power plant is rated at 15,000 pounds dry and 23,500 with afterburning. This gives a power-weight ratio at takeoff of 1.4 to 1. In contrast, the F-84F has a ratio of 2.4 to 1. Like other contemporary fighters, the 105 has a high concentration of longitudinal mass in relation to lateral mass. This means that motions due to inertia are more likely to couple with motions due to aerodynamic forces and produce violent gyrations. Whether or not this coupling is serious depends upon basic airplane configuration and stability characteristics. Directional stability was built into the 105 by using a ventral fin for effectiveness at high angles of attack and providing enough vertical area to compensate for conditions at high Mach numbers. Longitudinal stability and freedom from pitch-up are provided by the low stabilator position. The relatively high wing places the wake center lines progressively further from the stabilator as angle of attack increases. During flight test, an angle of 20 degrees has been reached. These stability characteristics, together with power loading, make it possible at low supersonic speeds for the airplane to hold or turn without losing speed. An actual history of a wind-up turn shows G's increasing to 5, while angle of attack increased to 10 degrees at a constant Mach number of 1.45. The flight test program has thoroughly investigated airplane stability and indicates that enough has been built in to provide a good weapons platform which is free from pitch-up and inertia coupling. The level flight speed envelope has been extended beyond predicted values at some points. Maximum Q reached in the extension test to design dive speed is 800 knots indicated at 6,000 feet. The high speed and kinetic energy involved create a deceleration problem. This has been minimized by extremely effective speed brakes, which make possible steep subsonic dives in addition to reducing the time required to slow down for safe emergency ejection. The rugged structure required for high Q fighter-bomber performance also provides pilot protection during this deceleration period without reliance upon complicated ejection devices. Assuming 550 knots indicated to be safe pilot exposure speed, it takes 10 seconds to decelerate from Mach 2 level flight. Longest times are from design dive speed, with 17 seconds required to slow down from 1.9 to 550. The same high kinetic energy, however, has taken the airplane to 63,000 feet, still going Mach 1.3 after a zoom climb with burner cut at 60. Calculations made using afterburner all the way indicate a 70,000 foot potential. This indicates that energy will be available at 62 or 3 for a firing pass at a supersonic bomber. Slow speed handling characteristics are also good, and the airplane has been landed with a 2,300 foot ground roll. For supersonic air induction, the design must consider the reversal of flow behavior. At subsonic speeds, compression causes higher velocities, but in supersonic flow, compression reduces velocity. Supersonic flow also changes velocity through shock waves, either oblique and weak, or of most concern, strong normal shocks perpendicular to flow, which are characterized by subsonic speed downstream and a large pressure loss, the magnitude of which depends upon the upstream speed at which the shock occurs. If we did not prevent this normal shock from occurring at airplane velocity, a Mach 2 design would probably not reach that speed, since only 72% pressure could be recovered downstream. If we first slow upstream speed to about 1.4, however, 96% recovery is possible. The F-105 uses a novel swept-forward intake to compress the air and slow down velocity before allowing the normal shock to occur. In the more conventional cheek duct arrangement, the air is first compressed outboard and then turned back to the engine, thus losing some efficiency. The 105 intake compresses air inboard only. This allows a thin root section, giving less drag and reducing vortex effect on the stabulator. A sliding plug positioned automatically according to Mach number provides the correct rate of air deceleration. Fuselage bleed doors, positioned by Mach number, air temperature, and angle of attack, provide the means of spilling excess air to match engine requirement with inlet area, thereby controlling shock wave position. This prevents excess air from shocking over the wing, creating drag. In effect, inlet air is compressed and slowed down before the normal shock is allowed to occur, and the shock wave is positioned by controlling expansion on the subsonic side. Another air inlet in the 105 is in the vertical fin. This inlet directs cooling air into the aft section. When this air reaches the ejection nozzle, it is at comparatively low velocity and high pressure. Therefore, it acts as the divergent section of a convergent-divergent nozzle. This reduces fishtail effect and base drag. The fire control system for the 105 has been flying in a modified RF-84F for about 2 years in accordance with the weapons system development concept. It furnishes the capability for both gunnery and rocketry, either air-to-air or air-to-ground, plus dive, level, and labs bombing modes. The versatility of the system produced an average CEP of 1,000 feet in the high-toss IP mode and 280 feet in the radar-ranging low-toss. A central air data computer feeds the fire control system. It also actuates flight control, making the 105 an integrated weapon system capable of automatic flight to the target, semi-automatic ordnance delivery, with a future capability of fully automatic store delivery. The first store drop program was conducted by Special Weapons Center personnel. Repeated, predictable, and accurate drops were made. In addition to labs deliveries, level ejections were made at speeds from 0.9 to 1.73. Faster capabilities will be explored at Eglin, where the program is now underway. During ground tests of the T-171 gun, long bursts at the 6,000 round per minute design rate produced dangerous gun gas concentrations which limited air firing to short bursts. A redesigned purging system is being tested at Eglin. The weapon system would not be complete without due regard for maintainability. Many features have been built into the airplane to aid in this work. Wherever possible, similar equipment has been grouped in bays with large access doors. Mach 2 equipment, however, requires extensive specialized training. Toward this end, over 227 military personnel have already been trained in the various phases of maintenance. To help them in their job, special tools and ground handling equipment are concurrently available. The flight test program, in which many Air Force pilots have been involved, has not disclosed any basic configuration deficiencies. Several mechanical problems have been corrected during flight test, and other hardware changes are being phased into the test inventory. Tactical Air Command is now scheduled for 3 aircraft in October 1958.